I'd like to talk about an inverted pendulum problem. And I want to start from a basic inverted pendulum problem where I'm starting off with a force applied to it, mass on the cart, it's moving back and forth, there's friction here, there's another mass at this point on a pole of a certain length. I'm not worrying about the mass of the pole. And I want to take a look at this problem. And I know that I can actually get to this question with a whole set of parameters to a linearized form of the system. Now, what's interesting about it is then I can say, all right, once I've got these two linearized equations, I need to reorder this to really make this fit into a typical state space formulation. Well, what the problem I have here is I have a second derivative in y and second derivative in theta. You're like, that's a problem. A second derivative in y and second derivative in theta. So I need to I need to make those more independent, so I need to separate those out. Multiple ways to separate those out in equations, just a bit of algebra. But eventually here's two reorderings. One is dy dt equals to a whole range of things, and then d theta dt equals a whole range of things. Now this fits directly into the formulation I might want to use, where I'm going to say x is going to be y dy dt theta and d theta dt. The derivative gives me the second derivative, as I see here and here, and then I can start to put this into my actual form. Cool. And so therefore I can get the various terms. The 1 and 1 here basically are to represent the derivative terms, so I can, because these are effectively second order terms. And then my two equations go here and here. And so all is great, and this is a really useful system. And then I can even take these numbers and start plugging in values for this system. And you think, great, this is wonderful. Except I kind of noticed something here that might be important. Notice that on one of the columns, all of the numbers are 0. And we care a lot about having things being full rank in terms of the system. Put another way, if I have something that has no effect on the system whatsoever, I could just kind of remove it, which is then one less parameter to worry about, and you go, yay, I simplified my system, right? Notice all zeros here, almost all zeros here, and then there's just a 1 representing the derivative, and you think, maybe there's something in this y to dy thing that's a little bit strange. So what if I think of dy dt as velocity, and I just call it velocity and call it v, right? Well, it's dy dt, dv dt equals, just the second derivative term. So be it. Take it and plug it straight into these equations, this one and this one directly. No problem, right? The interesting thing is now I basically have just dv dt and v. I have d theta squared and theta to worry about. You think, well, that seems manageable. And so now I can rethink this problem a little bit. And so now this is a third order system for x. I'm going to redefine x this way, and dx dt equals to this. So anytime you actually can reduce your system down because you realize the number of state variables is actually smaller than you started, this is probably helpful to you. It is probably, 1, it's going to be helpful in the math. It's 2, it's going to be helpful to get some good framework of it. And it's just fewer things to worry about. So that's probably good unless you need a higher order system to solve your problem, in which case now you actually know that you need to go do something different. And so again, it helps you. You can take the system, and now we could actually plug in these values into that system, and this is the 3x3 system that we now get to work with. Very cool. It does turn out that this matrix that I get 3 eigenvalues, 2 are positive, 2 are negative, 1 is positive, which is really interesting to notice. So of course it is unstable in one dimension. Not surprising, an inverted pendulum we kind of expect is going to be unstable around theta equals 0, which is where we expanded this. But what's interesting is that the other 2 dimensions we have reasonable structure. Along one dimension, it's not strongly stable, which is interesting. And that's along the 1, 0, 0, that's the velocity axis. And so that's really interesting to know that gives us some information on what's going on there. All right, so then the question is, one, is this controllable? And this is the controllability matrix you would get. Again, being third order actually means I can make it be a 3 by 3, so I saved myself some work, yay. And then on top of that, I know that this will be rank 3. I get 3 eigenvalues for it, 5.7, 0.28, 0.14. So these are interesting because you kind of see where, which things have the strongest effect. The eigenvalue tells you what has the strongest effect. The controllability matrix times that matrix squared effectively is a form, gives you a form of saying what is the sort of signal power in terms of how much strength they have along certain axes. In terms of the effect of the controllability system, and we notice that on the velocity axis, it's not as strong as you might like compared to along the theta. In this case, it's going to be the change in theta, or the omega axis. So depending on how I would put this together, that might give me some sense of what I would put together, what sensors I would put together. That being said, now I'd also ask, where would I place the sensor? And let's assume I want to do just one sensor, right? I could do multiple sensors. It's a combination of it. But what do I see when I put one sensor? Well, I could look at it for 1, 0, 0, 0, 1, 0, and 0, 0, 1. This would be a velocity sensor, a theta sensor, and an omega sensor, so a change in theta sensor, right? And so when you look at that, you say, well, what do I get? Well, for this one, I get structure, all 3 are rank 3. I can get all of them to work. And then I ask a different question. Which eigenvalues are the ones that allow me to control this better? And not only eigenvalues to control, but which one allows me to reconstruct it such that I can get back and get to the controllability? Because notice here, these eigenvalues, in one case, are very strong. But then I got one that's really weak along the velocity axis. In the other case, I've got ones that are much more even. Which would I want for a particular system? It's an interesting question. It would depend a lot on what is my design for my controller, and then what would I want to have for my estimator. And then what is the relative cost, if I was doing an optimization for optimal control theory, of the sensors to the actuators and so forth. So the question's a little more complicated and arguably something for a little further conversation going forward.